So we continue. What do we know about the distribution of the sample mean? So, like I was saying in the part one, the distribution we often represent graphically, looking like this. With this is the density function. The height is the an indicator of the likelihood or probability of observing something. We really think of it as the area under the curve, so this is a lot of probability here. This is also probable. Out in the tails here, there's very little probability. The area is very small, so there's very little probability we would observe an X bar far out in the tails of the distribution. So what do we know about the sampling distribution? Well, under some assumptions that are given in chapters 2 and 3, the sampling distribution will follow the normal distribution. The normal distribution, as you recall, is defined by the mean and standard deviation. So if we know what the mean and standard deviation is of the sampling distribution, we'd know what its distribution looks like. Well, the mean of the sampling distribution is just the expected value of the sample mean. So we can write the expected value of the sample mean like this, the expectation operator we can take through the summation sign to the inside, so we have the sum of the expected value of xi. But the expected value of xi is just our 19.75. It's what our null hypothesis is. It's the expected value of an x, and by assumption and our null hypothesis, we think that the expected value of x, the expected age of a student, is 19.75. That's our population mean. We shouldn't have i's here. Sorry about that. So the expected value of x is just 19.75. So we know what the mean is of our normal distribution of the sampling distribution. What about the standard deviation of the sampling distribution? The standard deviation of a sampling distribution we call the standard error of the sampling distribution. So it's just a nomenclature, just a word we use. The standard error of the sampling distribution is to distinguish it from the standard deviation of the sample mean. Instead, we have the standard error of the sample distribution of the sample mean. Right, so again, this is all in chapters 2 and 3 of Stock and Watson. So the standard error of the sample mean is just the square root of the variance, and you've done in Math 8 and Almost 40 that the standard error of the sample mean is just the standard deviation of the sample mean divided by the square root of n. So since our standard deviation is 1 and the square root of 200 is some number, I think this is going to be 0.07, got cut off here. If I recall, if I made a mistake, I'll get back to that. But I think that's right. Let's see. The square root of 200 is about 15, right? So it's 1 over 15. So 7 times 15 is about 100, right? 7, yeah. So that looks about right. So that's our standard error, and now we can. Now that we know what the sample distribution looks like, we know that x, the sample mean, follows, so that's this tilde sign, means it follows the normal distribution with mean expectation value of x, which we know is, by assumption, is 19.75, and this is the standard error, so it follows that. That's the distribution. So it follows the normal distribution, mean 1975, standard error 0.07. So we're assuming that the null hypothesis is true, right? And then we're saying, suppose the null hypothesis is true. We got a sample mean of 20.15. So what we want to know is if this is the distribution of the sample means, here, if it follows this distribution, what is the probability that we would have a sample with a mean of 20.15 if the actual population mean is 19.75? So we want the probability that our sample mean is 20.15 if the true mean of the population is 19.75, and the standard error of the sample means is as we've given. So what's that probability? Remember, the probability is the area under the density curve. Now, the probability that the sample mean is a precise number, 20.15, that probability, remember the probability is the area, so the probability of any given number is infinitesimal for a continuous variable, because think about it, what's the probability that it's 20.15? Well, what's the probability that it's 20.152, 20.153, 20.157? So the probability for a continuous variable doesn't have any meaning for any particular value of a continuous variable, because the probability of something, a random variable, being exactly that value, 20.150000, is infinitesimal. And so what we're going to rephrase our hypothesis test in the following way. We're going to say, what's the probability of getting a sample mean as far away from 19.75 as 20.15? That is, as far away as 0.4 units. Remember, our units are years here because it's age of the students. So as far away as 0.4 units from 19.75. That is, what's the probability that we'd observe a sample mean that was less than 19.35 or greater than I maybe have my greater than signs, 20.15. So that's what's the probability would observe a sample mean that was that far away from our assumed null hypothesis mean of 19.75. So if we go back to thinking about our distribution, all of these outcomes in here, we're going to think of them as, we can think of them as being close to 19.75. They're within 0.4 of 19.75. So this is 20.15 and this is 19.35. So all of these are within the range, and these out here, including our 20.5 and including our 19.3, these are far away. So we're rephrasing the hypothesis test to be not what's the probability of getting a sample mean of exactly 20.15 when the true mean is 19.75, but what's the probability that we'll get a sample mean as far away from 19.75 as what we got, which was 0.4 far away from it. And we'll call this a two-sided test. So we'll be looking at either side. We'll be agnostic about whether our sample mean that we got was high, could have been higher, could have been lower. So we'll think of it as being far away from 19.75. So what is that probability? Well, the probability is that we'll get a sample mean as far away from 19.75 as 20.15 is far away from 19.75. So that's the probability. So if we look down here, that's the probability in these two tails. So the normal distribution is symmetric, so the probability that you're in these two tails is the probability that you're in this tail times 2, because the probability that you're in this tail is the same as the probability that you're in the other tail. So we just need to calculate the probability that you're in one tail and multiply by 2. I'm going to pause here and go on to part 3.